is Octave Cornet. I'm the directeur of the Centre de recherche mathématiques. Donc, je veux vous souhaiter la bienvenue à ce colloquium exceptionnel parce qu'il s'agit du prix CRM Fields PIMS qui va être annoncé aujourd'hui. So the CRM Fields PIMS prize has started in 1994. It was first only prize awarded by Fields and the CRM, and then it was extended to PIMS later on. And it recognizes exceptional achievements in mathematical sciences and research in mathematical sciences by a Canadian researcher. And it comes with a monetary award of $10K. And it reflects a spirit of collaboration among the Canadian mathematical institutes. And indeed, the Fields, PIMS, and the CRM are having many joint projects and initiatives, and this is one of the oldest and most important of them. And in fact, I was supposed to, apparently, following tradition, to present the check to the winner. But new administrative rules at my university means that I cannot have the check in my hand. It was sent by post. So now the winner, I want to congratulate Bálint Virág from University of Toronto, who is a winner this year. He received his PhD in 2000 from the University of California at Berkeley under the supervision of Yuval Perez. And since 2003, he is a CRC at the University of Toronto. He received many prizes and distinctions, a Sloan Fellowship in 2004, the Rollo Davidson Prize in 2008, the Coxter James Prize in 2010, and the John L. Sting Prize in 2014. So he was an invited ICM speaker in 2014, and he works in probability theory, in random matrix theory, random walks, and other topics. And his lecture today is about random plane geometry, a gentle introduction through bisectors. Thank you very much.
Thank you very much for the kind introduction. And so the topic today is random plane geometry. The work I'm going to talk about is joint work with many people. Among those, the people listed here, they're all graduate students or postdocs at Toronto. And Janos Shortman, of course, you know, is a faculty member here in the audience. So I'm going to talk about random plane geometry. I'm going to use bisectors as a tool to maybe get your appetite into this topic. Let me just first talk about bisectors. So we are really going to talk about geometry in the plane. Okay? So to the degree that I can actually reasonably quote Euclid here, it's proposition 10, which tells you how to bisect a given line segment AB. And as it says is, okay, what you do is you construct this equilateral triangle with vertices A, B, and C, and then you bisect the angle at C. In previous propositions, you have been told how to do that. And then where that line intersects the segment AB, that's the point D, and that's where you bisect. So there are two things that I want you to remember from this, and one of them is that the bisector is perpendicular to the thing that you're bisecting. That follows from this, although it's not proven here. The other thing is that the bisector is a line. In fact, that's what you're using in this construction. Okay, so we're going to see to what degree this is true in random geometry. That will be kind of my basic question. So I'm going to do the following thing. Okay, let's look at the graph of a convex function. And let's look at the bisector of this graph in the following sense. You have a point on the graph, you have the left part of the graph and the right part of the graph. A bisector is going to be the set of points which have the same distance. Euclidean distance, okay, from those two things. So as you see, this person is pushing that thing over there, and it's touching the right-hand side of the curve, which means that its center is to the left-hand side of the curve. Yes, so its center is to the left of the bisector, right? And when it touches exactly at that point, then the center is going to be on the bisector. Okay, and you can see from this that the bisector actually still perpendicular to the curve and is still a straight line. Okay, at least if you look at the part above the curve. So that's good. And one more thing, you can also tell the bisector has a asymptotic direction and is minus the derivative of the curve at that point 0. Here we'll call that point 0. Okay, so here's like you take a look at the graph of a non-convex function. So you can see that the situation is a little bit more complicated. When you look at which are the points that are actually the distance of the two parts, if they're like holes like this, then this curve is not, this bisector is not going to be a straight line anymore. You can see that, but it will still have an asymptotic direction, you can imagine. And if you think about it, exactly what happens, imagine blowing this circle up to something very big, then what you see is that the asymptotic direction, you can get it as follows. You look at this concave or convex up function. Look at its function. Look at its concave majorant. Okay, so it's the smallest function, infimum of all functions, which are concave and greater than or equal to that function. This thing exists as long as there is a linear majorant. And look at the derivative of that function at 0. I hope I convinced you of that. And that's going to be the asymptotic direction of this bisector. All right, so that's just a little bit of geometry. Let's look at random plane geometry. So random plane geometry there are lots of versions of it. And the version that I like to focus on is the one that's, in some sense, the simplest. So first of all, it's plane geometry, and then you perturb it a little bit locally, independently all over the place. Right? So there are lots and lots of models, and it shouldn't matter for the most important questions what model you look into. That's universality. I'll discuss this a little bit. So here is a model where you take z squared and assign edge weights 1 or 2 at random to each edge. And then you look at the shortest path, the length of the path, which is the sum of the length of the edges. This, don't worry about the embedding. This is just for aesthetics. Just think of it as being on the grid. So that's it. Here is a bisector. And what we're really interested in is some kind of scaling limit of this. So what happens if you look at this from far away? What do you see? So there's the simplest sense which you can take a scaling limit, okay, and that's just you kind of shrink everything down, or you look at it from far away by the same factor in all directions, and let's call that factor n. Right? So take 2 points p and q, look at the distance in this random metric from np and nq, so those points far away, divide by n. Okay. So this has been known for a long time that this thing converges. This is kind of a law of large numbers for these random metrics. By the way, this is called first passage percolation in probability, to some norm. So some limiting distance. This limiting distance is deterministic, and it's just a norm on R squared. Okay, and these norms are characterized by the unit balls, for example. So if you know a unit ball, it's some convex set, you know what the norm is. And then it's translation invariant, so it's actually a norm, not just the distance, right? So that's what happens. And by the way, there is a nice thing. It actually, so first of all, we know that this is true in great generality. A, B, we don't know a single model, single distribution of edge weights where we know what this limit shape is. Okay, in fact, we don't know any distribution of edge weights where we know that this limit shape is strictly convex everywhere. Convexity is true for any norm, but strict convexity, basically meaning you have no facets, okay, no straight segments. We don't know for any single model. So it's in some sense, it's well understood. In some sense, we don't know. So yeah, so it would be nice. There are lots of open problems here, as you can see. Another thing, so it actually does matter whether you have facets, and here is why. If you have a norm which does have these facets, for example, the L1 norm and the L infinity norm, right? The balls being squares, which are rotated. Then there are lots and lots of the shortest path between 2 points, right? If you live in a grid like I do in Toronto, you want to go from work to home to work, lots of ways to get there. It's actually fun because you have lots of choices without wasting your time. But in Euclidean distance, there is a unique shortest path, right? So if you know that you have this convergence to something that doesn't have any faucets, then one thing that it implies is that geodesics converge to straight lines. That's just a simple consequence. Okay, otherwise we don't know. Geodesic converge to geodesic in the norm, but that can be many things. Here it is just straight line. So in some sense, this answers the question: what's the scaling limit of these random planar geometries? But in some sense it doesn't, and let me show you in what sense it doesn't. So when you actually do a geodesic, I just did one, okay, between these 2 points. You can see that this geodesic actually doesn't turn back, and that's not necessarily a feature. It's just when I tried simulating, it never ended up turning back. But it could, in theory, turn back. Then you see some interesting curve, right? It's some kind of random curve. It's fluctuations. And you would like to take a scaling limit to which this fluctuation is captured. And you don't want just a straight line. Straight lines are interesting, but you like to understand this limit. And the scaling limit and the scaling in simulations, then there are also some really nice heuristic physics arguments that are fairly convincing, which tell you how you should scale. Okay, so it says that if you take this geodesic and you go sort of distance n, then you have to scale by n in that direction, and the horizontal direction you scale by n to the 2/3. This is called the 1-2 straight scaling. I see where the one is, this universality class in physics where you expect these things to hold is called the Kardar Parisi and Zhang universality class. And you hope that there is a random graph gamma. Okay, and this is the directed geodesic. So there is no first passage percolation model where we can prove this, but we can describe what the limit is. So that's already something. Everybody believes that where you should go, and we can actually have a good description of what this limit is. We also know how to prove that certain other models converge to this thing. Okay, and I'll give you what those models are. How would you prove a convergence like this, right? So if you have seen, for example, a proof of Donskoy's theorem, random walks convert to Brownian motion, right? So you have finite dimensional distributions. You say those converge, improve some tightness and continuity, and then you get the result. So here, we don't know any of the finite dimensional distribution in any reasonable way. Okay, so this limiting curve is actually quite different. There is like a 1-point distribution that has a formula which includes an infinite sum. That's the best we can do. So that's not a good way to prove convergence. I mean, we'll have to do it some other way. So that's and then I'll tell you what the basic idea is here. Okay, so let's look at this directly. So the basic idea is that instead of taking just the limit of the geodesic, which is an interesting curve, we actually take a limit of the entire metric, but not in the scaling where you scale it the same way in 2 directions, but you scale differently in 2 directions. And it turns out that when you do that, you actually get the limiting metric. It's going to be asymmetric. It's not going to, but it is the limit of the random metrics of the plane. What do we have to do, right? So here I'm going to tell you, I'm going to do a zoom into my zoom out of the random metric, but in an asymmetric way. So what does that mean? So you look at 2 points in the plane, xs and yt, and then you do this kind of zooming, and to the 2/3 x and s, and to the 2/3 y and t. Then when you look at this distance, there is something that comes from the law of large numbers. That's the first term, this n times t minus s. Plus there is some error, plus there is this random quantity lxyt, which is a limiting random metric on the plane. Okay. So this object we call the directed landscape. And there's a construction of this using something called Brownian last passage, which is a random metric with directions in it. So let's see, what do we know about this limiting object? So let me tell you. So again, it's some 4-parameter function. Okay, it's nice and continuous. You'll see to what degree. And one thing, it's not exactly a metric, because you see the left-hand side, you have a metric that satisfies satisfies the positivity. But then you subtract this n times t minus s, so it won't necessarily be positive, for example. It also will not be symmetric in the two parameters. But it satisfies the triangle inequality, at least with a minus sign. You see that there's a minus sign in front, and that's just because of tradition. So we do it for last passage percolation usually, but this is now, it's in first passage percolation. So it satisfies that the distance of a point to itself is 0. It satisfies the triangle inequality. And turns out that these two properties are essentially the most important things about metrics. So this is what, it's enough to actually think about it as a metric and do geodesics and things like this. And I'll tell you in a second how. Another thing that it satisfies is this kind of scaling variance. So remember, Brownian motion, for example, has this nice 1-2 scaling variance. If you change space and time, it's the right way, then you get the same distribution, and you have scaling variance here, which has a 2, a 3, and a 1 in it, and that's the famous KPZ 1, 2, 3 scaling. And finally, we can also describe the one-dimensional distributions, or I can tell you exactly what they are. And they are a little bit like Brownian motion. It doesn't matter which point you look at, right? The distribution is certainly the same up to some scaling and shift. Right? So here, the shift is, there is some mean term here, mean line term, and then there is a trace-of-Widom distribution, which is something comes from random matrix theory, which is scaled according to the time difference. So what is the time? Well, there is a certain direction in time, which was the long direction before scaling, where this distance is going to be infinite if you go in the wrong direction. Okay, that just comes from the scaling. It actually follows from what you've seen already. So the distance of points that are in the wrong direction are minus infinite or infinity, depending on the time, but points in the right direction, some good distance. Okay? So that's in short what this limiting metric is. And let's see. So universality, right? So what is we believe that this limiting metric comes from anything in 2 dimensions. Okay, and there are lots of models. There is first passage percolation, where you make a random distance, which you have seen. There's last passage percolation, where instead of minimizing distance, you want to maximize things. You want to pick up as many cookies as possible along the way. And that makes sense in the directed setting. So if you only are allowed to go left and right, left and up, for example, and then you try to collect as many cookies as you can. So those are the models that we can kind of understand. And it's very important that this is in 2 dimensions. We don't have any clue what's happening in 3 dimensions. It's very important that you have nice moments. If you have, it seems like you probably need 5 moments for this kind of thing to happen. So that's actually quite important for real-world applications. And then this is random geometry, and just like ordinary geometry has many applications that are not obviously geometry, that's also true here. So there are various particle systems that you can understand this way. You can understand Tetris without players, how the surface grows. You can understand models of infection, like the Eden model, Petri dish stuff. You can understand random Schrödinger operators, parabolic Anderson model, lots of longest increasing subsequence in permutations. I'll tell you about that in a second. Random matrices, which is actually the most mysterious connection that we only partially understand. Okay, so here is a real world picture. There's a path from Athens to Thebes, which was one of the original seats of the Pythagorean schools. And you see there's a random path, and it's formed by kind of humans and nature. And the fluctuations of this path are very interesting. It would be nice to actually develop a theory which would be kind of similar to the KPZ theory, but I don't think it would be exactly the same. Okay, so let's see what's a geodesic in the landscape, okay? In this directed landscape. So once you have a metric, you can usually, which is actually a path metric, and that's true in this case.
Okay, well, thanks very much. That's a help. Okay.
So then you can automatically define length for curves, okay? So what is the length of the curve? Well, what do? You take your curve, you subdivide it into pieces, right? And look at the distances between the endpoints of those pieces, add them up, right? And here, this is like a distance with a negative sign. So you take an inf instead of a sub over all subdivisions over the sum of these lengths. Okay. This thing always exists. It may be minus infinity, but it always exists. There's no problem with existence. And you say a curve is a geodesic if for all subdivisions, you actually have an equality to this inf, right? So that's what geodesic is. You're always going the optimal way. And so this way, for example, you can check that if you take any fixed curve in this random geometry, say you take a straight line, okay, the length of that is always going to be minus infinity. So, but there are some random curves which have finite length. So there is always good ways to go. In fact, any 2 points will have a geodesic in between them. And you see, the way what you can do with this object is measure the length of curves, and the kind of things that are used for are called one forms. So one way to think about this object is as a random one form in the plane. It's kind of the universal right random one form, and it's very non-Gaussian. It has its own rules. They're different. Okay, so what do we know? So we take, okay, so any 2 points have a geodesic in between them, and if it doesn't really depend on those 2 points apart from there's affine transformation, some affine transformations. So let's just look at the geodesic from 0, 0 to 0, 1. Okay. And let's see what does this look like. So if you look at something like this, and you're like me, your first guess is, okay, this is a Brownian bridge. So wiggly, it goes from one point to another, Brownian bridge. Okay, it turns out that's wrong. So in fact, it's more continuous than a Brownian bridge. It's always further 2/3, but any exponent less than 2/3, it's further there. And Brownian bridge measure assigns 0 mass to curves like this. So it's completely singular to Brownian bridge. It has 3/2 variation, just like Brownian motion has quadratic variation. And it's a limit of many integrable last passage geodesics, like Brownian last passage, various other models, Poisson last passage, geometric, exponential. There are a bunch of models that we understand a lot because we can compute almost everything. But this thing is still a new result. So it was a bit hard to get this result, but at least we know in some models which are similar to random geometry, or some versions of random geometry, we actually have this result. So we do have that this is the limit. And maybe the one that's simplest to explain and is not quite obviously a last passage geodesic is the longest increasing subsequence, this Ln. Okay, so if you look at a random permutation, let's see if I have, here's a permutation. Okay, you have the numbers 1 to 9. You permute them at random, and you look at its longest increasing subsequence. There may be more than one. In this case, 3, 4, 6, 8 is an increasing subsequence. Right? That's a list. So you're going to plot this list. That's what I did. The first element of the list is 3, then it's 4, then it's 6, then it's 8. So you get a curve like this. You want to understand what the limit of this curve is. Okay. And the answer is the limit of this curve is a straight line. Okay. But then you can subtract the same line and ask what's the limit of that. And that turns out to be this random function, the directed geodesic. And this is a new result. There's some very old results about, or 20-year-old results about the length of the longest increasing subsequence. Well, this is not about that. It's just the shape. The shape of the longest increasing subsequence in random permutation converges to the directed geodesic in this random plane geometry. All right, so I want to get back to bisectors. And I want to show you that this. So remember that this directed landscape distance had a mean term, right? And the mean term was of the distance between 2 point xs and yt was this negative y minus x squared over t minus s. So let's take with positive, and let's call that's also a directed distance if you throw away the noise. So let's understand what happens there. Okay, so this again defines the distance between points in the plane, right? Like that. And it turns out that if you measure the length of the path, just like the way we did before, right? The length of a path is going to be first of all, for a path to a finite length, it has to be a graph of a function, because you can go back. There was that. There's also here a can go back story here. Things are in the wrong order. You have infinite distance. And if your function is called pi, then it's just the Dirichlet norm squared. That's the distance. That's the length of a curve. And that defines and then the shortest curve between 2 points is just a straight line. Well, you know, Dirichlet norm with those boundary conditions is minimized by linear function. And by the way, if you want to look at what the ball is in this distance, okay, so the points that are distance at most some number from a point, it's actually a parabola and everything above. It's still convex. And the center of the ball is the tip of the parabola. So you can still, by the way, there's a ball, there are two balls because it's asymmetric. It's one backwards, one forwards. The other one is also a parabola, surprisingly. Okay, so here's something nice that you can do with this Dirichlet distance. That's just the one that we looked at. So let's say you have some object far away in the plane. Okay, and let's say that at this, say, let's call it time s, you know how far the distance from that line is from the object. So how far the points in that line are from the object, from your boat. So it turns out that if you do that, then you can also, just from that information, these distances, you can tell how far you are at a later time t. And the way is that basically, you know, basically that when you do the straight line to the closest point, then it hits this other line at s, and then from that you can just check that the way you compute this distance is so the new distance hyt is just supremum over hxs minus, I think maybe I looked through it, this is maybe the negative distance. Let me see if I did this correctly. Yeah, I think it's the evolution of the negative distance, okay? Minus this distance between the 2 points that are on those two lines. Okay, this is just optimizing the triangle inequality. And when you look at this, you notice, oh, this is something, maybe you have seen it. And this is just a Hopflex solution of a simple PDE, which is the Hamilton-Jacobi equation. Okay, but the simplest version, simplest Hamilton-Jacobi equation there is. Okay, so that's not completely random because actually Hamilton-Jacobi equations were developed in physics to understand evolutions of distances, or actions is how they are called. So you know, when you study Hamiltonian dynamics, this is one of the standard objects, and there's an action defined, which is basically a distance between points, and you see how that evolves. That's the Hamilton-Jacobi equation. And in fact, you don't have to start with an object. You can just start with some function at time s, and you can evolve that function. So you can start from some initial condition h0, and then you can define how this thing evolves. Okay, so there's a little bit of, you know, simple PD in a second. Okay, so what happens when you do bisectors with this Dirichlet distance? You can ask. And well, the bisector again solves this equation that the distance from the left-hand side of your function h is equal to the distance to the right-hand side of the function h. Now here is the thing: if you look at this negative distance h, then its derivative with respect to x satisfies the corresponding equation that they get from the Hamilton-Jacobi, and that's the Burger's equation. Now, if you've seen Burger's equation, one way to solve it is by understanding characteristics. Okay, and it turns out the characteristics in the Burger's equations are exactly these bisectors. Okay, so there is like a connection between PD and all this story, and so that's kind of and I'll tell you in a second what this means in the random setting, because it's quite interesting. It's also true in the Dirichlet metric that the bisectors have asymptotic direction, and the limit and this asymptotic direction is exactly perpendicular to the concave majorant of the function. There's a 1/2 there just because of some scaling here. All right, so let's look at the same story. Let's look at what we did before. We did this kind of Hamilton-Jacobi equation, and let's do a random version of it. So let's see how a distance evolves in this random metric. So your sky is a little bit hazy. So as you go farther, there's some randomness coming in on what you see from that boat, right? So it turns out that when you do this, and you see how this evolves, you have a function that evolves, right? Which is just the distance at the time. This random function is a Markov process, turns out. That just follows from the fact that the parts of this random metric are independent over time. So when you evolve, you don't care about the past, you just keep going. And that this object has been studied, and it's called the KPZ fixed point. And there's a beautiful formula by Matitsky and my colleague Jeremy Castell and Ramanik about how this thing evolves. They're beautiful determinant formulas that describe the evolution of this. And then the way you can think of this equation from what you've seen before is that it's the simplest version of a random Hamilton-Jacobi equation. HT is HX plus some funny noise, which it's been an open question for a very long time of how to make any sense of something like this. And it was not difficult to make sense in this case, but now we know how to do it. We can actually add the noise to this equation and analyze it after that. All right, so let's see what are the bisectors in the random geometry, right? So let's start with some function h, and again we're asking what happens when you're equidistant from the left-hand side of the function and the right-hand side of the function, right? So these bisectors solve that equation. The two distances are the same, right? The bisectors, can think of them as the characteristics of the random Hamilton-Jacobi equation. You can't really express these with derivatives anymore, by the way. It's a little bit harder because things are a bit more rough. All right, so here's a little bit of a picture of the bisectors. So the gray things are geodesics to this bottom straight line from a given point. This is a discrete version of the geometry. So you see I drew a geodesic from every point. These geodesics, they coalesce. So this forms a forest, right? And the bisectors are actually boundaries between those forests. So the green lines are bisectors. The bisectors between certain initial conditions. All right, so that's about it. Now I want to tell you about TASEP, okay, because this is another story. So TASEP is the simplest particle system in the world, okay? And let me show you how it works. So it was basically introduced by biologists in the late 60s. And they're trying to understand how there is like materials going through cell membranes and how that kind of transport happens. They go through narrow channels, and when they go through narrow channels, there is traffic jams. But it's not the only place where it happens. For example, there are papers which studied this with mRNA. You may have heard of this thing, mRNA, nowadays. Yeah. So in mRNA, there is this gadget called the ribosome, which takes the mRNA, reads it, and produces whatever it needs to produce. But there isn't just one of them, there's more. So they also form traffic jams. So you study that using TASEP. So that's TASEP, but what is the dynamics? So basically the point is, look at this left thing. So what I do is I represent, so there's either a particle or a hole on every side on every integer location on Z. Okay, so it's a one-dimensional model. Every point, either a particle and a hole. If there is a particle, I'm going to draw a little up line. Okay, if there is a hole, I'm going to draw a little down line. Okay, so that's how you get this thing. That's called the height function. So what happens is particles like to jump to the right at rate 1. So independently of each other. And they do that jump as long as there's nobody there already. Okay. It's really, it's hard to come up with a simpler model of a particle system, and it's already very complex and beautiful in its internal structure. So the way you think about it in terms of height function is that every little peak, right? It's a particle and a hole in front of it where it can jump, just turns down with rate 1. So this thing kind of goes down. So how do people understand TASEP? And one of the tools that you try to understand TASEP is second-class particles. What's a second-class particle? So TASEP, right, has particles, and you like to understand the movement of particles. But the problem with the particles is that they're not really the right object to study. And here is why, right? Because you have this kind of profile which slowly evolves over time. So you can see what happens. And what the particles do is they just go zoom away from you because they always go in one direction, much faster than the profile evolves. So particles are not the right objects. They're just too busy. It's a little bit like you don't study waves by seeing what the water molecules, right? That's a little bit similar to that. So they introduced a kind of particle which captures the height function. Okay, and here is how it was. Here's one way to define the second-class particle. You can just define it as a little valley. So if you have a little valley in your initial condition, throughout this evolution, you can follow what happens to this little valley. Because the only thing that could essentially happen is one of the sides of this valley gets flipped down, right? And when it's flipped down, you just say, oh, the valley moved to that point. So here is like xt is the second-class particle. And it turns out this is it actually captures what happened. It's sort of the reason you do this. And here is one beautiful theorem due to Kipnis and Ferry from almost 30 years ago, which is that if you look at the asymptotic direction of where this second-class particle goes, so you look at xt over t, and it satisfies the law of large numbers. So there is, with probability 1, there's an asymptotic direction. Well, this asymptotic direction is random. So it's a kind of funny law of large numbers, right? Maybe you've seen it in Feuerzern, for example, but right, it's a random asymptotic direction. And in fact, not only it's random, it has a uniform distribution in the interval -1, 1. And it's been kind of a little industry to study what could be the direction of this second-class particle. So lots of people have worked on this, and there's some beautiful papers. So let me tie things a little bit together. So one thing that we proved with Master Z is the following. So if you start with this Tay-Seb function, and there is a second-class particle in there, this Tay-Seb, you apply it to the whole system, a KPZ scaling. So look at what happens from far away. Okay. Then, but you have to do it in a way that the initial condition of the Tay-Seb, so you started with some particle configuration that converges to some function h0. So you do a scaling like that. Okay, then the second-class particle, then the trajectory of the second-class particle is xt, converges to the bisector in the random geometry of that curve. Okay, so that's another reason why you care. The second-class particle will be the bisector. And now you're really interested in, okay, well, what's the direction of these bisectors? How can you compute? So let me tell you. Okay, so let me tell you what is the directions of bisectors in random geometry. So first of all, the direction, it's a mild conditions, but the initial condition actually exists. So there's always a random direction that the bisector goes. Second, the bisector looks almost like a geodesic. It's not actually exactly a geodesic, that's not true. So it's not real. Geodesics is the analog of straight line, right, in the random geometry. But it has this property that if you just look at it in a compact set, then the two things, well, then the bisector is absolutely continuous in law with respect to the geodesic. So structurally, it's kind of locally the same. There's a lot of information contained in that fact, because these curvy, these fractal-like structures, their absolute continuity class tells a lot about them. All kinds of things like law of iterated logarithm and all those things are almost true properties. So they all get transferred. Okay, so let me tell you some examples. So let's say that I start with an initial condition, which is a full line. So it's a function with some slope, or just asymptotic to that. Okay, then the direction of the bisector is going to be again perpendicular to that, and it's not random. It's deterministic. So that's one fact. Here's another fact. So let's say that your initial condition is just 2 points. Okay, the function is maybe -infinity everywhere and just 0 at this point. So what is the bisector? Turns out the direction is random this time, and the law of it is normal. It's normal distribution. Okay, well, it's the first time we see normal distribution in this talk, by the way. But it sometimes comes up. Okay. Okay, so here's another question. Let's say that I take a line segment, right? And I look at a point, maybe not necessarily in the center. What is the distribution of the law of the direction of the bisector? So it exists again. And here's what the direct distribution of the law is. You take a uniform random variable, you take a chi5 random variable, take a beta 2 random variable, and take a normal random variable, make them all independent, and take this formula. That's the distribution. yes, so Sergei Pirov, okay, there's a question I can answer. So the answer to that, what is H0 plus and H0 minus? They're the left-hand side and the right-hand side of the initial condition. And you have to be equidistant from the two. So, well, these formulas are kind of crazy. Let's tell you where they come from. Okay, so actually, we have a general formula for any initial condition, as long as they're kind of sublinear. Okay? And here's what the general formula is. It's very simple. You take your initial condition, okay, it's some curve. You add to the initial condition a Brownian motion, two-sided Brownian motion. So it will be followed at first, but it will become a little bit wiggly. Now you take the concave majorant of that object, and your direction will be perpendicular to that. So all those formulas that you saw before just came from that, right? We take these objects like the 2 points. Well, when you put a Brownian motion to that, well, it's just going to be two normals. Concave majorant, well, that's just going to be the slope, right, connecting those two normals. So it's just going to be a normal. And the other formula, where does that come from? Well, turns out that if you look at Brownian motion in a finite interval, you can compute the law of its concave majorant to some degree. You can compute the slope. And this is all due to actually quite recent work of Jim Pittman and Waki, who have a beautiful conjecture about Brownian motion and its concave majorant. Okay, the beautiful conjecture is that if you look at twice the concave majorant minus the Brownian motion, so it reflects the Brownian motion up from its concave majorant, then it's a Bessel phi process, which is the radial part of a 5-dimensional Brownian motion. Okay? And this is to be compared to the celebrated Pittman theorem, which is if you, instead of the concave majorant, you do the running maximum and you do the same thing, then you get a Bessel III process. That's a theorem. And in their paper, Pittman and Waki, they're able to do partial results here. For example, it's true for a fixed time. And they also understand the slope of this majorant. So we were able to use their result to get these formulas. Okay, so maybe I'll stop slowly. How much time do I have? Really? Okay, so I can chat. Don't worry. So yeah. Okay, so the summary of this is the following. So bisectors in random geometry, they're not straight lines, but they're a little bit like it. They're locally absolutely continuous with respect to straight line. Well, they're in some sense perpendicular to the initial conditions, right? You just have to add this Brownian motion and put this concave majorant. And they're in fact capturing what the T-sub second class particles do. So that's in short what the random geometry bisectors are doing. Okay, so maybe I'll say thank you. I was a little bit fast, so I'll ask questions, and then maybe through the questions I can continue. Yeah.
Thank you very much. So, of course, if there are questions, first I'll ask for questions from the room, and maybe there are some other questions on Zoom.
So, what was the initial condition that gives just the uniform? I assume you can reconstruct this original uniform -1,1 from the concave.
Yes. So if you start from an initial condition which is not deterministic but random, and the way it has to be random is that it's Brownian motion with different slopes. Okay. So let's think of a two-sided Brownian motion plus a negative absolute value function. Okay. Then the direction is uniform. Yeah. Even in the limit. That was actually kind of a surprise to us because the uniform actually comes quite a bit from the discreteness. But there is still a way in which you can reconstruct this.
I have two questions. The first one, what is the process M, which appeared in one of the last theorems? And second, is that, yes, M.
Yes. So,
and second,
so can you see if I write here? Can you make it? Can we make it see? Yeah. Okay. So think about, here's your Brownian motion, right? M is the running maximum process. So let me take a color chalk here. So this is B. M is the running maximum process. And this 2M minus B, just the way you imagine it is you take these things when you go under the blue thing and reflect them up, okay? And so on, right? So this would be 2M minus B. Okay, And for K, right, you know what K is. You just have Brownian motion. And now, I don't look at the Ramming maximum, but you look at the concave majorant, which is just something like this. These processes are very different, right? This process, how should I say, is the place where it's not linear functions. So the set of places where it increases has Hausdorff dimension 1/2. It has the same law as the local time of Brownian motion at 0. This process has actually the place where it decreases is a discrete set of points, except at 0. The only uncontribution point is 0. So this is the place where it's not really linear. So it's a very different thing.
Second question is in one of the last sentences there was B prime, but it's not derivative. What is it? B prime.
B prime. Yeah. Okay. Let me see what was. Yeah. So what this formula is, you take the initial condition H, right? You add to it this curvature 2 times the Brownian motion. Look at its concave majorant. Right now, this is mostly just straight lines, line segments, and they differentiate that. So that's it's a derivative, but not of the Brownian motion.
Thank you. Yeah, thank you.
Right.
At one point, you talked about moment conditions that were important, like 5 moments maybe were important. I don't know if you could comment a bit more on that, or
yes. So I like to think about it in terms of to what degree does KPZ describe real life, right? How hard is it? So that actually has to do with moment conditions, because like you want to see how rare events, how rare they are in real life, right? How rare is it that you construct a road? Well, not too rare, right? So when you look at this curve from Athens to Thebes, that actual road doesn't quite look like a KPZ curve. Okay? And I think the reason is the right way to model it is to kind of figure out what are the tails of these rare events, like I don't know, mountains and so on, and roads and so on that are constructed, and then find the corresponding model. Right? So just like there's Brownian motion and there's stable processes, there is the analog of Brownian motion would be directed landscape, but there should be processes in between for various moments. Right? And there are some very extreme moments where these processes are understood. They're basically just last passage percolation in the limit with some invariant point process. You can actually just collect points. There is a way to do that. But the intermediate ones are not understood yet. And those I think would be very interesting to actually describe what you do see in reality with these random roads, or with these actual roads that are shortest path. So the moment condition is just, it's very hard to say what it means at the moment because we don't have any results that are like CLT. We don't have universality results in last passage percolation or first passage percolation. But it seems like that you can modify your existing models without changing the moments that much that the limit will not be this, or there will not be the limit in the same sense. There's also that. So yeah, there's a whole lot to study even theoretically, and I think one of the most interesting questions is what other models of random geometry are there, which would reflect this kind of, because like CLT is very common because 2 moments you easily have, but 5 moments, well, okay, right? That's
right. Thank you very much. Maybe there are more questions. The room or from away from.
I wonder if you can go back to the forest picture. So the forest was built by building geodesics in which sense?
Okay, good question. So you look at geodesics. So for every point, right here, you have all kinds of paths to this bottom line, right? And you look at, say, the shortest path, and you draw that.
So the forest was generated how then, or?
Sorry?
So you generate the forest first, and then you generate.
Yeah, you generate the forest by writing for every point. Okay. You draw the shortest path to the bottom line, right? So then if you have 2 points, as you can see, these things coalesce. So there are lots of theorems about this, how the coalescence happens. Okay. There's a whole different talk I could give. It's quite amazing that a lot of things are very, very different in Euclidean geometry and the random geometry. And then And then the green things, so this is the forest, and then the green things are the boundaries of the trees. And those correspond to bisectors, because those are the things where, you know, like if you go on this side, you better go on that side of the green thing. If you're here, you better go on the other side of the green thing. So it's exactly the equidistant things. And they're actually bisectors between two small points near where the things land, if you want to make it very precise.
I'm sorry, there was something strange in the formula with derivative of h plus b. It was taken in the point 0, but what is 0?
Well, 0 is, so 0 is where I split the curve, right? I'm interested in what's equidistant to the left side of the curve, so the negative parts on the negative axis and on the positive axis. They just, you can split at other places and then you look at it, would like get the derivative somewhere else. And by the way, I don't know, it's an open problem whether this is true jointly at two different points. So at 0, we know that this is true. Jointly at two different points, we have two, you know, both sides make sense. But I don't know if the answer is the same. We don't know how to prove it, so we haven't found a counterexample.
Okay, let's thank our speaker again, and congratulations for the prize.